All right, so it's my pleasure to welcome Derrick Turk. He's the president of Terminus Data Science, and he lives in Houston. And before that, he was CTO at Enertel Advisors, and then also an engineer at Devon Energy. And he did that for about 5 years. Previous to that, he was at the University of Texas at Austin. And we actually overlapped for a year there. I was there 2002 to 2005, and I think you started in 2005. Is that right?
That's right. Yeah.
So you were a mechanical engineer, and I was over in chemical. I think the unique thing about UT Austin is that there are separate buildings for each department. So chemical engineering had its own building, the CPE, shared with petroleum engineering. And mechanical engineering had its own, how many stories was it? Like 8 stories?
Yeah, it was 8 or 9. Just those 70s style Soviet blockhouse buildings. They were pretty great.
Yeah, we overlapped a little bit there. So one of the things that, and one of the reasons why I wanted to have Derrick come talk to us is he has given other presentations as well, been very involved in the energy, oil and gas industries, and really has a unique perspective on data science and machine learning, and wanted him to come and talk to you. Now, a lot of the students here in the class are in engineering, but also cybersecurity. We have a geology major here as well. So it's kind of a number of different disciplines from chemical, electrical, mechanical, civil, and then some of these others as well. So Derrick, welcome, and I'll go ahead and turn it over to you for the presentation.
Thanks. I'm very happy to be here, and I really appreciate the introduction. So that's correct. I'll actually begin with a little bit more of how I got here and sort of how I went from engineering to whatever it is I do now, which they tell me is data science. So I've always had programming as a hobby. I've always loved building things on computers ever since I was a kid. And in fact, even as a teenager, I really thought, oh, I'm going to go into programming. I'll study computer science. But I graduated sort of in the aftermath of the .com bust. And so people said, well, there's no future in software. Studying engineering, that's much broader, much more applicable. And my logic was, well, I'll study the most generic possible engineering field, the one that kind of opens the most doors or can be used in the most different ways. So I thought as a teenager, which I decided was mechanical engineering. And so I studied Mechie at University of Texas. And I graduated in 2008, just as the financial crisis kind of hit. I was aware of the oil and gas industry because there are people in my family who've worked in it. And even some of my high school friends, I'd heard a little bit about oil and gas companies hiring and so on. And probably most of you won't remember, but sort of immediately prior to the big crash in 2008, oil prices reached just incredible all-time highs. And long story short, I'd kind of done a little bit of advanced planning and taken some courses my senior year in that industry and lined up an internship. And so the oil and gas industry kind of became my escape route. And I found myself a kind of a trained mechanical engineer, semi-reluctantly working in the petroleum industry. And I rotated through a few different disciplines within that industry. But by about 2010, I found myself working as what's called a reservoir engineer in a new ventures group. It was what we called it. So new ventures meaning the group inside the company that went out and identified new opportunities and assessed them and decided, should we get involved? How much should we be willing to pay to get involved? What can we expect to achieve if we do invest in, say, drilling in this new asset or buying an interest in an existing asset? So one of the things that kept kicking us over those years at Devon Energy is where I was, which is an independent E&P, meaning exploration and production company. independent in this context means not big enough to be vertically integrated. So unlike the Exxons or Shells of the world, we didn't own any refineries or any gas stations. We just found and produced oil and gas. And that required us to understand, as the geologist in the room will probably understand, to understand flow physics a little bit. So if you're a mechanical engineer, or maybe even a civil engineer, you know that the Navier-Stokes equations describe fluid flow under various conditions. They're this kind of horrible set of differential equations that we can really only solve under specific simplified conditions. And we have solutions for special cases. And we try and sort of take everything we do as engineers and make it fit into one of those special cases so we can apply whatever the special case solution is. Well, in petroleum engineering, we worry mostly about the flow of what we would call viscous and compressible fluids, oil and gas, in other words, through porous media or rocks. And this special case is Darcy's law, which is of course not the Darcy's law I've shown here. That's a different Darcy's law entirely. But it's this, it relates the flow rate through a porous medium to what's called the permeability, sort of the ability of fluid to flow. Really, Darcy's law almost defines the notion of permeability. We think of permeability as the ability to flow fluid through a porous medium at a given viscosity and pressure differential. So in the New Ventures group, we try to apply numerical simulation. This is a finite element or a finite difference method. And in school, we always learn it in terms of what we kind of call a layer cake model. In the real world, it can be a little bit hairier. The reason it can be hairier has to do with the big shift in oil and gas in the United States from what we would call conventional reservoirs to unconventional reservoirs. And what we really mean is shale oil and shale gas. So the best analogy I have is if you think of the rock containing the oil or gas as a cake, a layer cake, a conventional reservoir might be something like a tres leches cake. It's a nice, airy, spongy cake, and it's full of milk and cream. And if you want that milk or that cream, you can just poke a straw into the thing and sort of slurp it out. It's not that hard. That might be like a sandstone formation that we might produce offshore in the Gulf of Mexico. Shale might be more like a brownie that's soaked in chocolate liqueur or rum or something. And what's worse is this brownie, it's not baked very well. It didn't rise. It's really dense and chewy. It's almost fudgy. And so if you want to get the good liquid out of the brownie, which you really end up kind of having to do is take a bendy straw and run it along the long axis of the brownie, maybe poke some holes in the bendy straw, and use an electric pump to force water or liquid into the brownie to crack it on the inside so that you expose some of the surface area of that dense, fudgy brownie so that the chocolate liqueur can actually flow. And that, in a nutshell, is hydraulic fracturing. That's what the fracking process is, and that's why we have to use it in shale oil and shale gas situations, because the rock has a lot less porosity, which is the sort of the sponginess or the amount of holes in it, and a lot less permeability. It's a lot more difficult to flow fluid through that rock. And so as a consequence, when we try to simulate these things numerically, we're not modeling a nice layer cake with a single straw poking into it. We're modeling a very heterogeneous brownie with a lot of little fracks and cracks that we've created with properties that are kind of heterogeneous and anisotropic. In other words, they vary depending on where you are in the rock, and they vary depending on which axis you attack it from. So it becomes really, really difficult, even when we have the equations, or at least have a finite difference model, it becomes really difficult to solve these things from a physics-based or a mechanistic point of view. And that kind of leads us to, let's go and apply machine learning instead. Because as they say, correlation does not imply causation, but it sure helps. Sometimes it's all we have. Sometimes we don't have the data needed for a mechanistic understanding because the rock is too complex, or because we simply can't measure the properties we need. But we do discover that the dependent variable, the thing we care about, which is usually measured in dollars, can be reliably predicted from the things we can measure and from the things we can control. So we can use this to solve optimization problems too. The way I stumbled into this is through my other hobby, which when I got into it in the early 2000s, we still called AI. I bet a lot of you probably already know, this is not the first AI and machine learning boom. This isn't even the second AI or machine learning boom. We're on about number 3 or 4, depending on how you define it. In particular, there was a pretty big boom in statistical learning methods in the 90s. Even in the oil and gas industry, they got some adoption. And the limitations really became our inability to plumb huge amounts of data through these algorithms. And so when people talk about big data in a modern context and deep learning and things like that, what's new and what's changed is not necessarily the volume of the data, although that has increased. It's also sort of the fit for purpose of our hardware and our algorithms to apply these techniques to data sets at that scale. But long story short, I had some experience playing with things like genetic algorithms and stochastic optimization back when that was big. And I kind of followed the slow reemergence of statistical learning methods, things like neural networks or support vector machines or random forests. And these are a really perfect fit for these big ambiguous problems we faced. So in fact, it was so perfect that after a few years of applying these techniques inside an existing organization, I realized there was an industry-wide need for these skills. And I went independent as a consultant in 2013. I launched Terminus Data Science, LLC. And that's run as a one-person operation for many years. In this last year, we actually grew to a 2-person operation. My wife, Catherine, joined me. Her background is in the chemical manufacturing industry. And she brings a lot of skills in predictive maintenance and in sort of understanding the logistics of huge capital projects in manufacturing to our business. So with that, I'm going to present a short case study that sort of illustrates some of the opportunities and some of the challenges in applying data science and machine learning to the oil and gas industry and sort of more broadly to engineering problems in energy. And I'm going to state my thesis up front, which is that the hard part of data science is turning data into information. So this case study comes from the ancient world of 2015, before the shale apocalypse, the great crash, sort of driven by the glut of production that came out of the Permian Basin in subsequent years. And this was done for a client that was another independent oil and gas exploration and production company. The problem, they were managing an unconventional oil basin, in other words, a shale oil asset. And they wanted to use predictive models to sort of think on the margins. And what I mean by thinking on the margins are answering questions like, can we cut a little bit of cost and lose only a small amount of productivity? Or can we increase productivity in underperforming areas by doing some kind of cost-effective intervention that we identify? And also, can we more accurately value our acreage? Because they had an eye to maybe flip some of these assets to other companies. We didn't have big data. We had what I like to call small weird data. Only 108 wells, we say completions, but really 108 oil wells, for which we had data on how much they made, how they were fracked and drilled, and some rock properties. In other words, the petrophysical data, meaning the porosity and permeability of the rock. So as we often do, we began with a cluster analysis, and it sort of actually, I should say the first step was really to do some exploratory analysis to sort of visualize the data and understand rough patterns in it. But we like cluster analysis because it helps us avoid Simpson's paradox. We never want to fall into the trap of finding trends that appear to hold when everything is lumped into one big bucket, but which really break down when you identify meaningful subpopulations. And so we applied k-means clustering. And based on similarities in geologic and completion parameters of these wells, we identified several groups, and we kind of tagged them as the really good stuff, the okay stuff, the rest, and then this oddball group of just huge fracks where we pumped a ton of fluid and proppant, and they kind of behave very differently. We like to feed that through principal components analysis, because one of the big challenges we have with what I call small weird data is reducing the dimensionality. When you have 100 observations and maybe 50 variables for each observation, that's not really going to work well for any modeling approach that we have. So you want to identify a smaller number of meaningful factors. And that's where things like PCA and factor analysis come in. And so we were able to identify 3 or 4 sort of synthetic variables or principal components that really explain the bulk of the variance in this. And it's always fun to visualize things in 3D, both because it helps us as humans, we're very visual creatures, and because clients like to see it, they think it's cool. It is cool. So we came out of this exercise with some questions that guided our modeling approach. First, we noticed that no group showed a very strong relationship between the frac design, the completion design, and the performance. So why was this? In particular, in some of our best wells, we noticed that performance was almost totally invariant to frac design. We also discovered there was a missing variable, and we kind of got this by talking among the engineers. One of the keys that comes out of this is domain knowledge. It's not enough to just apply machine learning or data science techniques in a vacuum. You really want to bring in the domain experts, the engineers that really understand the problem physically. And they pointed out that we hadn't captured the distance between wells. Wells can interfere with each other. They can drain overlapping volumes of rock. And so we wanted to account for that in our modeling exercise, which meant that we had to program. We had to write some software because we did not have the frac data in a convenient format. We actually had to go in and quote unquote digitize. These were PDFs, but they didn't contain tables or nice graphs. So we had to sort of turn these pictures into quantified data. Stage by stage, we pulled out what we call the log net pressure versus time data, which is sort of what the pressure you read at the surfaces as you pump a hydraulic fracturing job, as well as the volume of stuff we were pumping. And we applied some transformations to that along the way as well to turn it into features. This was really a big feature engineering exercise. And so this was kind of the pipeline. And I'll get to the moral of this story in a second. It's not necessary to really go into excruciating detail, but in short, we had PDF frac reports. We built a Python script to pull the SVG graphics out of those PDFs. We parsed the SVG files to find the relevant lines on the plots. And then we sort of translated those back, given the known axes of those graphs, to coordinates. We then had a script written in the Julia programming language that would come along and try and identify segments within that curve, which followed straight line trends, because those straight line trends and their slopes have meaning inside the domain of hydraulic fracturing. And so by consulting with our frac engineers, we worked out that we needed to identify periods where the pressure was on say a unit slope linear trend or a negative 1/2 slope trend. Both have meaning in that context. And then finally, we extracted metrics of those segments into our machine learning model as new features. And I always think of a quote from one of my favorite writers on programming. He has a small software as a service app, but he calls it the programmer's credo. We do these things not because they are easy, but because we thought they were going to be easy. And that's kind of the tar pit we got into here. And you can see our segmentation algorithm in action. It's kind of identified regions within these pressure plots that have straight line trends. So that, and then we were able to build a simple script, another programming exercise to capture well density, turn that into a spacing metric. I'm sort of blowing through this because it's not super interesting unless you're knee deep in completion design. But the point is that we really had to think about how to extract and engineer features. It's one of the hardest parts of machine learning in practice, is that your data set as provided doesn't necessarily contain the metrics that really matter. Sometimes you have to do some clever or tricky or at least domain informed things to get those. And so what was interesting to us is we were able to actually identify that well spacing did make a difference. And it wasn't a continuous relationship. It was almost a thresholding relationship. Once wells were denser than a certain threshold, there really began to be a strong negative impact of drilling wells too close together. And so in the end, we were still only able to explain about 60% of the total variance in performance. That's another recurring theme in engineering applications of machine learning, is that the success case can still be significantly less than the 0.99 R squared, which people sometimes like to show off for, I hate to say toy examples, but let's just say more tractable problems. And so we live with that. And the reason we can live with that is that, like I said at the beginning, the goal is not really to have a perfect predictor. The goal is really to have a model that captures relationships in the data so that we can think on the margins. In other words, we're less concerned about being able to plug in, the well goes here and we pump this much liquid and this much proppant, and it's in this formation and we make this many barrels. And we're more concerned about, okay, if the next well in this sequence, we ramp up the frac fluid volume by 5% and we cut the proppant loading by 2%, about how much change in production can we expect? And so, I try to coach my clients that it's more about understanding how the system reacts as you turn the knobs that you can control as an engineer than it is about trying to make perfect predictions. And so some of that may be a story for another time. But the thesis I actually take away from this, and the biggest thing I want to share with you today is that, and I believe looking at your course syllabus, you guys are lucky enough to benefit from similar thinking on this. If you want to learn data science, machine learning, AI, whatever the current buzzword is for these kind of data-driven techniques, the path starts with programming. There's no getting away from the need to build custom code to manipulate data, to, sometimes I call it clean up data, but I think of it less as cleaning and more of finding the information in the data. Everything from discarding erroneous readings to finding new calculated features that are more useful for a machine learning model, to incorporating some of the domain knowledge from engineers or geologists, or even supply chain experts or financial planners. And if you're an engineer, you're probably already a programmer, and you're certainly well equipped to learn those skills. In fact, you are already on that track. And as you've surely seen, you really learn it just like any other engineering skill from the fundamentals. There's no magic, there's only engineering. I tell people this a lot. I coach a lot of engineers who are trying to enter data science or enter programming, and all their engineering skills carry over. That same mindset is all you need. And in fact, I really believe programming is an engineering discipline. We solve concrete problems under constraints. We apply quantitative techniques, and there's also a lot of room for creativity, just like in engineering. In fact, I like to think that you can kind of make analogies and fill in your own favorite discipline here, that the pieces, the parts, the concepts we work with in programming sort of form a tower of abstractions, just like we do in an engineering discipline, working our way up from our understanding of physics and chemistry through our understanding of materials and mechanisms to an understanding of machine design and systems. And the same is true in software and in programming and in data science and in machine learning. So all that said, I really think that ML, machine learning, and data science will play a huge role in the future of energy, both in the fossil fuel industry and in renewables and other sectors. In fact, we've already seen that geothermal energy involves many of the same challenges as oil and gas. And solar and wind energy involve a lot of mechanical engineering, obviously, but also a lot of predictive maintenance, especially when you think about wind. A lot of moving parts in those systems, right? A lot of rotating equipment, and a lot of the same techniques that we use already in things like chemical manufacturing to understand when rotating equipment needs to be maintained and how to identify problems before they start by machine learning carries over. So I'm very optimistic for the future of these fields and the future of engineers applying these techniques to solve problems in them. So I believe that's about all the time we have. I would like to take questions for the next few minutes. So this is my Q&A bingo. I've kind of filled in common questions I get from engineers, and we'll see how many of them we hit. But feel free to ask anything you'd like.
Hey guys, we gotta get bingo here, so questions. All right, Zach.
Okay, so you said to, kind of start programming, and as you said, a lot of us have, obviously if we're in this class, we are at least familiar with one or two languages. but how do you know like what next we should start learning in programming fields?
Yeah, that's a great question, and it's actually not one I have on my bingo board. So, I guess the answer I would really give is that there's no substitute for practice, right? Um, no matter what sort of organized curriculum or reading list you find, there's really no substitute for just jumping in and uh, doing projects, right? Building things that matter to you. And so it's kind of a cop-out answer. But I would say find a problem to solve that you're interested in, and the rest will sort of come naturally. That will guide your research. If I had to give a rough reading list, or in particular, if I had to weigh in on what I think it is that most engineers who enter programming through data science miss, I would say that they tend to come in through languages like Python or R, and there tends to be a very applied, library-heavy focus to the way it's taught. And so I would say what's sometimes missing is the fundamentals, data structures and algorithms, and also some of the tools of professional programming that can make our lives easier. Things like version control systems or automated testing or type systems and type checking. These are all ways that we can bring sort of an engineering sensibility to building robust software. And ironically, I don't think they're often taught to engineers. But like I said, I think the best overall advice is just to solve a problem you care about and sort of let the rest follow as it will.
And I also saw a slide up there that said Python, Julia, and R on one slide. So I think you're doing
Yeah.
good.
Yeah, we work in a large number of languages, and some of the reasons for that are to fit in with clients' existing systems, and some really comes down to just trying to choose the right tool for the job. And we could get into sort of what makes certain tools right or wrong for one job or another. But one thing you do find is that, I would say all those languages are really quite similar, actually. Once you've sort of seen a couple dozen others, they really look the same. They're all dynamically typed, interpreted languages that don't really require that much sort of mental retooling to jump between.
All right, so this is less about machine learning, but more about your decision to go and create a consulting firm. I'm a little curious about that and why you decided to go that route. And what do you think you're doing?
Sorry, one second. I'm going to have to turn my volume up. I didn't mean to close the screen share here. Give me 1 second. I've got to bass boost the the speaker here so I can hear.
Yeah, sorry, it's a microphone that's in the classroom. But Mark's question was, what made you decide to go off on your own? I mean,
Oh, thanks. Yeah, so what made me decide to go up on my own? That's a fantastic question. And it's one which I suppose I will hedge between the real answer and the sort of corporate acceptable answer. Sorry, 1 sec. I'm trying to make sure I've got the right screen up. But not that it really matters. So it was a combination of a push and a pull. And the push was realizing that in the role I was in, I really had sort of limited ability to make the changes that needed to happen to get our sort of data science effort on a track that can make a difference. In particular, and I'm not trying to knock my previous employer, but we were really fixated on the idea of bringing in outside expertise, bringing in statistical consultants, provided in fact by our statistical software vendor, and sort of putting them in a closet, siloed, and letting them churn on the problem for 2 months. And what would happen is they'd come back with a report that would be like copy and pasted from Wikipedia for the first half, and then a model that didn't really work and didn't really solve the right problem would be we sort of tacked on at the end. And it just struck me so deeply that the people who needed to solve these problems were not consultants or software industry people. They were the engineers that had their hands dirty in the problems in the first place and really understood, going back to correlation does not imply causation. the way you disentangle correlation from causation is by understanding the mechanism, by understanding the actual system you're trying to model, right? And so we have a lot of examples in oil and gas of ways it's easy to pick up the wrong end of the causal stick, to find a model that correlates Y to X and insists that X causes Y, but really X and Y are both caused by some underlying confounding variable Z, or maybe Y even causes X, right? We accidentally use the future to predict the past a lot, especially if we don't have that hands-on experience. And so long story short, I saw a need for engineers who had these kind of crossover skills to really help companies do this the right way. And, the opportunity was right, the timing was right. I wanted to move back to Houston for a lot of different reasons too, and I just kind of pulled the trigger.
All right, Denver. Hey, Derek, so you talked a lot about how domain knowledge can kind of impact the way that you create the models kind of thing. Can you talk about the process of, like, say you have a certain domain knowledge and then putting that into the models? How does that go?
Yeah, so I would say three main ways, three different ways that can come in, 2.5 maybe. One is just what I said before, which is your knowledge of what can possibly cause what. In other words, you've got some mental model of the causality of the system in your head. That's what's going to keep you from building a stupid model, right? That's what's going to tell you what's an independent variable and what's a dependent variable, and what's a useful predictor and what's not. To give an example, this is a dumb one, but I've seen it. I've seen a commercial software company come into the oil and gas industry and pitch a piece of software that uses a suite of variables that you know before a well is drilled, plus the well's production in its first 6 months of history to predict its long-term total production. And it's like, we can already do that. We already know that, in other words, most of the information about how well a well will produce is determined in the first few months of production. So they're sort of using they picked up the wrong end of the stick. They've used something that at the point that, you no longer need the model, and kind of patted themselves on the back for, oh, we got an R squared of 0.9. So one is just to avoid stepping in traps like that. The other is it can help you engineer features. It can help you sort of create new variables from your data, which you think have physical meaning. And an example of that in traditional engineering might be something like Reynolds number, right? The observation that you can combine all these properties of a flowing fluid system into one number that sort of captures the ratio of, oh Lord, this is how long it's been since I was an engineer, the ratio of kinematic to, well, someone's gonna have to help me on this. I guess the propensity for laminar versus turbulent flow, right? Someone had to notice that was a useful quantity to capture in that context. And so by applying things like PCA or factor analysis, our domain knowledge can kind of guide that process. The third, or maybe the 2.5 way, is I'm a big fan, I didn't get to talk about it in this deck, of Bayesian approaches. And so in a Bayesian approach, we actually explicitly model our prior knowledge about a system. We may literally write down, like in reservoir engineering or in production forecasting, I may write down probability distributions describing what I believe the true distribution or the expected distribution of flow parameters should be for a given oil or gas basin. And in a Bayesian inference approach, we may kind of have that as a piece of a big hierarchical model or a big linear model. And we point a Bayesian inference process at the combination of our pre-existing beliefs, our prior probabilities, and new data as it's observed. And what comes out the other end of the Bayesian machine is a posterior distribution, an updated belief, what we should now think about the world by integrating what we originally believed with what we observed. And so I think there's some computational limits on what we can do with that right now. But I actually think the holy grail for machine learning and engineering will be the ability to apply Bayesian techniques at scale and maybe integrate Bayesian techniques with some of the work that's already been done and is really impressive on things like deep learning. In other words, the ability to fit complex models at scale.
I have a question. I'm the token geologist in here.
Okay.
I do research in source rock geochemistry. And I've tried implementing some machine learning techniques, and they haven't been accepted very well due to loving everything being so interpretable.
Yeah.
Models aren't as explainable as people like. And so I'm sure that you've had, clients that have wanted explanations on why the model predicts. So what have you done to do that?
Yeah. So, right, explainability is a long running battle in machine learning. And I'll sort of state my bias up front because I live in the geology world, you're actually lucky in a way. You truly do have big data. You have sets that are amenable to things like deep learning. In the reservoir engineering world, we have small weird data. We have limited observations and sort of heterogeneous data sets. And so in my day-to-day life, I'm actually pretty biased in favor of simpler models. I really like ensembles, so I fit a lot of random forests. But they do still have the same problem of explainability. And the way I approach that, some people will say, well, fit simpler models to the model, and then you have an explainable proxy. I think that's kind of weird. What I like to do is I like to visualize the response surfaces. What I mean by that is, say you've got some model that has 10 features, 10 inputs, and 2 outputs, right? Or 1 output, I guess. Let's keep it easy. So what I might do is for each of those 10 inputs, I might say I'm gonna for each of those inputs, I'm gonna hold the other 9 constant at their mean, and I'm gonna vary that input from its min to its max, and I'm gonna plot what my prediction does. And there's ways you can make that more sophisticated, right? Instead of using a min to max and holding the rest at the mean, you can sort of try to do like I don't know, an imputation or somehow honor the kind of the joint probability distribution. But what you end up with is 10 different surfaces, 10 different slices that show how Y responds to incremental changes in X. And that goes back to what I mean by reasoning on the margins, right? So I find that decision makers, explainability is a little bit of a misnomer. It's not that they want the model to be explainable per se. It's that they want it to be less of a black box that tells them do X, Y, and Z, and more of a utility for saying, okay, we're already doing, X and Y. What's the Z we can add, right? Like what changes can we make and how does the system respond? And so the more you can build that and the more you can make it interactive or even like 3D, bring in more dimensions at once. I've had a lot of luck with that approach. You can also fall back to a simpler model. One thing I like to do is fit Bayesian hierarchical or Bayesian linear models. They don't necessarily have the same predictive power, but what's really nice is they are actually pretty straightforward to explain. You say, well, if you make this incremental unit change in X, you expect this incremental unit change in Y, and the uncertainty on that slope is known too in a Bayesian model. You have a distribution for that beta, for lack of a better word, that coefficient. There's actually some pretty good communities for machine learning and software development in geoscience. There's one I know of, this is not an advertisement, I just started poking around them a few weeks ago, and there's a lot of chat, is called Software Underground. I see a lot of geoscientists and geologists talk about ML and visualization and Python programming on there and sort of compare notes.
So, Derek, I just had a question for you. You mentioned sometimes you want the machine learning model to not only say these are your inputs, predict this output, but then also tell them, like in your case study, which wells should we keep or what should we do next? What can you say about like applying machine learning models and optimization? Does it work well? Or do the optimizers find structural weaknesses in the model?
Yeah, so that's a good question, because it can be very dangerous to just sort of turn I guess a general optimization routine loose on the response surface of a machine learning model. One of the biggest limitations we have in ML is we always find it very challenging to quantify the uncertainty in our results, right? And in particular, there seems to be this sort of hand-wavy inverse correlation between how complex and powerful the model is versus how well we understand the uncertainty coming out of it, right? Like take something like a deep learning approach for image recognition. You get a score out of like, oh, this is 79% cat, 35% dog, 2% car, 3% grilled cheese sandwich. But you don't necessarily have that kind of meta information of what the uncertainty in the certainty is, right? So I'm pretty reluctant for that reason, especially when I think about typical situations in oil and gas, where the R squared of the model may be like 0.6 to 0.7. And we already know that at the extremes of the data, the data set's very sparse. And so even though we may not be able to quantify it, we know that the model has a lot of uncertainty in it at the extremes of the input domain. It makes me a little reluctant to just say like, okay, here's a global optimizer, go find the minimum. What I do think you can do is sort of take the sort of domain knowledge given best practice or what's typically done and perturb it, right? Look for sort of a more local optimization approach of, okay, well, you know, we're in a high density region of the domain and we're pretty confident in at least the direction of these correlations. So, you know, can we turn knobs incrementally until we hit some kind of local maximum? That I think is a little bit safer than sort of black boxing it and just running like a global optimizer. The same problem actually comes up in a portfolio analysis, which is another thing I've dabbled in for a client where, you sort of hit limitations in your ability to model all the real constraints in a corporate project portfolio. And if you just let a global optimizer like a min-LP solver or something loose on it, it will come up with really creative and really physically impossible project schedules because there's just physical constraints that are missing. And until we get better at sort of encoding those or capturing constraints and uncertainty in our modeling process, I think there's always a little bit of hands-on supervision that's needed.
So earlier, you said that you sometimes use, I guess, when you said that Y actually causes X, and so you sometimes use future data to predict past data. I didn't understand what you meant by that.
Oh, yeah, my point is just that that's a common mistake. It's a mistake that's easy to make if you don't have the domain knowledge to understand the problem you're trying to solve. Is I often see people come in who don't have experience in the industry or in the problem, or don't talk to the engineers actually working it. And they'll sort of fool themselves, right? They'll build a model that seems very powerful, has a high predictive ability, but then you discover that they've accidentally baked in one of the outcomes that you're trying to predict as an input to the model, if that makes sense.
Okay, that makes more sense. Thank you.
Yeah.
What about grad school? Do these students need to do grad school to do data science?
Yeah, that's okay. That one is actually on the bingo card.
I actually said that question, assuming that it would be on there.
Yeah. So my answer to that is I don't know. I would say be cautious because it's kind of a gold rush we're in right now, and I see, to be honest, my joke gold rush stamp is more written kind of with an ear to boot camps than it is with grad school programs. But I get nervous because I see these boot camps popping up and charging fairly steep admission, if not sort of locking you into indentured servitude by putting a lien on your future earnings. And it's like, again, I'm thinking more of boot camps. So I find often with the boot camps, at least, well, all they're teaching is Python and pandas, and you can learn that by reading documentation. Now, I think if you've got a program that's really sort of framed from a you know, I guess better way to answer it is what would I look for in a grad school that would make me say like, yes, this is a program worth pursuing? I would say it needs to focus on the fundamentals, meaning the fundamentals of statistics and machine learning, and be sort of less fad or tool oriented. I find that the tools come and go. It was R 10 years ago. This year it's Python and Pandas. 10 years from now, maybe if I have my way, it'll be some dependently typed language. But who knows, right? Those come and go. What doesn't come and go is the fundamentals of statistical modeling and understanding things like overfitting and model validation and the curse of dimensionality and all these sort of intrinsic constraints of the universe that we work with, as well as the fundamentals of programming, data structures and algorithms, right? I mean, that's the superficials change, but that doesn't. And so I think if you find a program that doesn't just spend its time on the superficials, that could be great. But I see a lot of boot camps popping up that charge, $30,000 or $40,000 to take you through a very superficial tour of one or two Python libraries, and I don't think that's good value for anyone except the boot camp.
Okay, well, I think we're about out of time. And thank you so much for your presentation. That was excellent. I really like the perspective, especially the themes about applying engineering knowledge and bringing domain expertise into data science and machine learning. I think that's a fantastic thing to hear about. Focus on fundamentals, the algorithms, understand why you're doing something versus just treating it as a black box. And I really like your career advice as well. You've worked at a big corporation, but also independently, so you have kind of a unique perspective. So thank you so much, Derrick. I really appreciate it. And let's give him a round of applause.
Thanks for having me. It was fun. I love seeing engineers get into machine learning and software development. We need more of it, more interdisciplinary crossover. So it's very exciting to see.
Okay, thank you.
All right, thanks.